Great. So today we're talking about Gauss's law, and we're going to go over several different applications of them. This is a big one. So hopefully this will be something that if you need to, you can go back and review. There are also a lot of videos online too. So maybe you'll find somebody who does things better than I do, and that's totally cool with me. But I did want to point out that I assigned the FRQ for Unit 7 gravitation. So that went up today. That's 4 problems altogether. It's one bit of a doozy, but I'm going to give you some hints on it today because it definitely relates to Gauss's law as well. So we'll do that towards the end, but I'll be really clear about the hint when it comes up. Yeah. Um, I could try and write a little bigger for you. Okay, well, here we go with Gauss's law. The secret is right here. How can we make this easier? So choosing the best surface will make that step easier. So E dot dA, there are a couple of things that are happening here. So number one, there's a dot product. So anything we can do to make sure that E and dA are parallel to each other would be great. We also have to be mindful about the direction of dA. So when we have a closed surface, dA always points outward. I think we had there was a homework assignment yesterday where it was a practice work where we had a little bit of question about the plus and minus. And I think it had to do with the direction of dA. Right. So it can be a little ambiguous when you have a flat surface, but with a closed surface, dA always points outward. So that's very important. Now we're going to take a look at 3 different geometries today. And these are 3 fundamental geometries. They are planar and cylindrical and spherical. And we're going to take them, we're going to hit them all today. So planar, and now I'm going to leave some space here, and cylindrical, and then spherical. So let's just take a look at what happens with those different geometries. I'm actually going to start with spherical because I think that's the easiest one to imagine. So let's suppose we have some uniform sphere of charge. I'll put some positive charges in here. And then our Gaussian surface of choice is going to be a little sphere. Because for the charges that are enclosed, the electric field is going to be radially outward. So that's the direction of our electric field. It's radially outward. And obviously this is supposed to be spherical, so theoretically they'd be coming at us on the near side and going away from us on the far side. So it's going to be convenient for us to talk about an overall charge Q, but in this particular example that we're going to do in a little bit, is that we're going to have charge that's spread out uniformly through the sphere, just like mass on our planet is essentially uniformly spread out throughout the sphere of our planet. Some little variations here and there, but in general. And so the gravitational field is always inward, which is really interesting. I was thinking today, I don't know, I don't want to go too far down this road, but you know, we talked about how there are positive charges and negative charges, but what about mass? Is there positive mass and negative mass? And then the other thought is, well, maybe it's all just negative mass. That's why the gravitational field is inward. And since you're multiplying two masses together, you could probably represent mass as a complex number, that when you multiply it together, that one of the terms is going to generate I squared, and that would be the minus sign. I don't know, just interesting things that theoretical physicists think about. All right, well, anyway, what is this going to look like? We would typically ascribe a charge density, and that would be the Greek letter rho. Rho would equal charge divided by volume. So when we do E dot dA, the integral of E dot dA on this closed surface, then we see that E dot dA, E is parallel to dA, and E is constant. So with this choice of a Gaussian surface that matches up with the geometry that we're dealing with, this integral becomes instead E comes out of the integral, and it's a scalar now, it's not a vector. And then we're just doing a closed integral over the area of a sphere, right, which we know how to do. So initially this looks pretty scary, but if you choose the right Gaussian surface, it's actually a piece of cake. So for cylindrical, this would the electric field, so if we have a uniform charge distribution and it's a sphere where R is constant, then the electric field is going to be a constant as well. Yeah, and also we can assume that the charges that are outside, since they're not enclosed, then they don't have a role, because remember this came about because of electric flux, right? So the net flux caused by the charge that's outside. So this is exactly true. The FRQ that you're going to see in gravitation talks about a planet, and then you drill a hole all the way down through the planet, then you let go of a rock. And the rock, you can show, will actually oscillate back and forth. Because as the rock descends, the gravitational pull is only caused by the mass that's closer to it, to the center. It's not caused by the mass outside. Because, for example, if you think about some kind of position that the mass that's outside the position of whatever the object is going to be pulling you outward in this region, but it's going to be pulling you downward in this region, and the net cancels out. And we'll talk more about that in a minute. Now, in the cylindrical situation, imagine that we have a row of charge. Then the electric field is going to be pointing outward. And again, we did an example like this where we had two rows of charge. And then our Gaussian surface is going to be a cylinder. So when you're doing the area of a cylinder, you have the area of the side, and then you have the area of the ends. But you can see if this is infinitely long, if this charge density just keeps on going out towards infinity, which turns out to be the same place, then when we do the integral of E dot dA, then same thing. On the side, like, a paper towel roll when it's all used up. On the sides, E is parallel to dA and constant. So we'll just have B equal to the electric field times the surface integral over the side of a cylinder. But on the ends, the electric field is perpendicular to dA, so E dot dA is 0. So that makes the cylinder a good choice for an infinite line of charge. And then finally, for a planar geometry, so I'm going to attempt to draw a sheet of charge. Yes, that's the whole point. Yeah. Right. So the end game for applying Gauss's law is actually figure out how the electric field is going to change. So, right. So if E pops out of the integral, then I can figure out what the area is, and then I can figure out how the charge enclosed works. Then I can figure out what the electric field is going to be. E dot dA. E is parallel to dA and constant. Mm-hmm. Okay, good. So what kind of surface would we use for this? And the answer is we're going to use a cookie cutter. So we're going to take a cylinder, and it really could be anything. I say cookie cutter could be, like a star or, a square or a heart, whatever you want to be. But then when we take a look at the electric field, we assume that the sheet keeps on going forever in all directions. So the electric field is just going to be upward and then in the bottom downward. And so it's sort of the reason I chose a cylinder is because it's a similar argument that we made here. So when I go E dot dA, the sides, now you can see dA for the sides would be coming outward, but they're going to be perpendicular. So the electric field would be perpendicular to dA. So E dot dA is equal to 0. And it's at the ends where E is parallel to dA and constant. So once again, E dot dA is just equal to the electric field pops out, and then we're just integrating over that surface. And the surface would be the ends, but we can also just call that A. It really could be almost anything. Okay, so I'm going to pause here. We're going to move on to the next sheet. And then for each one of these, we're going to break it out and take a look at applications. But this is just a discussion about the geometries we're going to use and why we choose the Gaussian surfaces that we do. Okay, so one more time, planar symmetry. And I also should talk about the charge density too before we go on too far. Here, typically we would, for cylindrical geometry, we would talk about a linear charge density. So lambda equals Q over L. And then for planar, we would talk about a surface charge density, which we usually represent by the Greek letter sigma, which would be Q over the area that we're discussing. All right. So anyway, when we see this, these are the typical ways in which we represent how much charge is packed into that sample area that we're choosing for our Gaussian surface. Okay, here we go. Let's do the planar one in more detail. Planar. Okay, so once again, we'll take a look at, we have a big sheet of charge that goes off to infinity. And in electronics, this application is really significant. So I guess it's my job to show you why it's significant. Above, we have electric field pointing upward, and below, we have electric field pointing downward. So as we mentioned, we're going to choose a Gaussian surface that is a big old can. And as we go upward, we can see we have electric field coming outward here, and then as we look down below, we have electric field going downward. Okay, well, as we mentioned, when we go to apply Gauss's law, because we have a smart choice in our Gaussian surface, then that's just going to be EA, where A is the surface. But I have two of them at the top, and I have the bottom. So there are two of them. And even though the electric field on the bottom is pointing downward, dA is also pointing downward. Yeah, so we get two of them. And then that's got to equal the charge that's enclosed divided by permittivity of free space. Okay, well, let's simplify this then. So 2EA is equal to Q, that's enclosed, divided by epsilon naught. And then if I want to get electric field all by itself, which is the whole purpose of applying Gauss's law in the first place, we're just trying to find out how the electric field is going to be affected by this charge distribution. And so it's going to be equal to 1 over 2 epsilon naught times Q enclosed over A, but then we'll recognize this simply as the surface charge density. So that's equal to sigma over 2 epsilon naught. Top and bottom, yeah. Right, so remember dA is always outward. So outward on the top is up, and so is the electric field. And then on the bottom, dA is outward means down, and the electric field is also down. So they're both contributors. Now let's do two planes. Let's have, I'm going to try and get too fancy here with my drawing. It does not depend on the distance of waveform. It's uniform. It's a constant. It doesn't depend on distance. Now again, this is a bit impractical to say that these go off indefinitely, right? But let's take a look at this example with two planes, and then you can see where this is a good approximation to real life. So I'm going to say on this top plate, I have a positive charge density plus sigma, And then on the bottom plate, I'm going to have a negative charge density, negative sigma. Okay, so I have two plates of charge, positive and negative. This, my friends, is what we call a capacitor. So remember yesterday, flux, and then today is capacitor. Yay. This is one of the most important devices in electronics. And I'll show you why in a second. Okay, so we're going to assume, as far as electric field goes, that we have electric field going like this. And then we have, for the negative charge, we have electric field going like this. But this is what's called a linear space, and in linear spaces, the superposition principle holds. So the net electric field that you get is simply the sum of both. So we just found out that the electric field for a uniform plate of charge is sigma over 2 epsilon naught. Shouldn't the negative go in? Well, hang on. Yes, the negative should go in. Thank you. Inward. All right, and then so let's go ahead and move forward on this. So the electric field that's outward on the top part is going to be sigma over 2 epsilon naught. And then the electric field that's going downward is also going to be sigma 2 epsilon naught. And then we're going to have an inward field that's also sigma over 2 epsilon naught. And then inward, which is up down here, which is going to be sigma over 2 epsilon naught. Now I'm not really satisfied with this. I'm going to draw a little bit bigger just so we can settle that in. So let's enlarge it. We'll make the distances a little bit further apart. Okay, once again, so negative sigma, positive sigma. Right, so in this upper realm, I'm going to see an electric field that's upward. And the contribution is going to be sigma over 2 epsilon naught. And in this region, the electric field caused by my positive charge is going to be downward. And again, the electric field caused by the positive charge is going to be sigma over 2 epsilon naught. And then down here, in this region, the electric field caused by the positive charge is still going to be downward. And so that's why I've drawn all these in red. Now let's take a look at the relative direction that results from our green. So in this region in between, we know that the electric field is going to point towards the negative charge. So that's going to be this way. And again, the electric field is in the same quantity. So these two are going to add together. But in this region, the electric field caused by the negative charge is upward. So they're going to cancel. And then above, the electric field that's caused by the negative plate is still going to be downward and uniform, so it doesn't depend on how far away from the plate we are. And then I think you can see what happens. So in this region, they add together. In this region, they cancel. So this is what our net electric field is, 0 on the outside, sigma over epsilon naught, because we added these together and then 0. So there's an attractive force between these two. And so if we put this together in a circuit, and we're going to use a lot, we're going to do a lot with capacitors. They're really cool because what they do is they pile up positive charges on one side and negative charges on the other. And they tend to want to stay there because there's an attractive force. So as an example, if you had a voltage that was changing and you fed it into a capacitor, what you get out is a much smaller wave, or just no wave at all. So they have a tendency to smooth signals out. So if you have a surge protector at home, it's got a huge capacitor in it. So if you have a big spike, somebody turns the electric dryer on and it causes a spike in your household circuit, then your capacitor is going to fill it in. So that's one application of capacitors. Capacitors actually act like mass. And so anytime we can draw a physical analogy with an electrical situation, that's a win for us. Okay, good. So that's planar. Yeah, this question about resistors, how are they going to work together? And yeah, absolutely, they would work together, but that's more for timing. In terms of smoothing signals, you don't really need a resistor. All right, cool. So what's next? So cylindrical. Find E due to an infinite line of charge. So let's do our plus signs here. I'm going to do a few positive charges here to represent our infinite line of charge, off to infinity, off to negative infinity. It doesn't really matter who's on which end because they're the same place. And then our electric field points outward. I could do it all the way down the way, but just enough. And so we set up a cylinder that cuts through the electric field lines. So we already talked about this in the intro about how a cylinder is going to have no flux on the ends and only flux on the sides, and then the electric field can come out of the integral. So when we apply Gauss's law, E dot dA, so we're going to do the side only. Ends equals 0. So we're just going to do the side of our cylinder. E dot dA is, well, E is parallel to dA, so that's just, there's no cosine. It's the main point. And E comes outside the integral because it's going to be constant as long as it's a uniform radius. And so we're just going to integrate the side of a cylinder. And that's equal to the charge enclosed over epsilon naught. Now the charge that's enclosed is going to be equal to the length, or at least depend on what the length is. So if we've defined a linear density, that means lambda would equal the whole Q divided by the length. Then the charge enclosed is just equal to our linear charge density times the length. Okay, let's go ahead and do this integral. So the parameter here is a circle, so that's 2 pi r, and then I multiply by the length, and that's it. So E times 2 pi r length. And again, our goal is to find out how does the electric field change. Now, when we did planar geometry, it was just a constant everywhere. But here, as we get farther away, we'd expect the electric field is going to get weaker. And so we set this equal to lambda L over epsilon naught, and you can see the L's are going to cancel. And we get something very similar to a point charge that we did yesterday. So I divide both sides by 2 pi, so that's 1 over 2 pi epsilon naught. And then the L's cancel out. And then I'm going to have lambda over r. Right, so it falls off as 1 over r with our infinite line of charge. With a point charge, it's 1 over r squared. It's 1 over 4 pi epsilon naught times q over r squared. Right, so we see some real consistency here in the geometry. Right, so planar constant. Linear falls off as 1 over r. And point charge falls off as 1 over r squared. But when we do the spherical geometry, we're going to take a look at a couple of different cases. Okay, so any questions here? Give you a few seconds to take a look. Oops. Yeah, so there's a question about how did we use or how did we not use the area last time, right? So we certainly could have used the charge density over here when we were talking about the planar geometry. But you can see that when we do this integral, since it's just the integral of dA, that is the area. So this could have been anything. Could have been a square, could have been, you know, starfish, right? Could have been a Christmas tree cookie cutter. It doesn't really matter. Because when we cut it out, we still have an A. And then on the other side, the charge that we have is just the surface charge density times the area, so the areas cancel out. Right? So it didn't matter what the shape was, really. But we kept the cylinder look because it's really similar to what we just did. And this treatment right here is about, you know, the fact that E dot dA is 0 on the sides and it's just EA on the ends. And then we kept that when we took a look at this. Right? We kept that argument. Now it's 0 on the sides and it's a number on the ends. Okay, cool. All right, here we go. Yeah, this is a big one. Glad you're here for this one. And now let's do spherical. We'll do a couple of examples of spherical because there's a lot of things going on. Spherical, let's call this spherical 1. And we're going to be inside a insulator with uniform charge distribution. Okay, great. So what's that going to look like? Well, again, I'll just attempt to draw this again. So we have some kind of big old sphere, and then our Gaussian surface is a smaller sphere on the inside. And we assume that the contributions from all the positive charges around it are zero because they cancel out. So the only charges that count are the ones that are inside. That's Q enclosed. But again, because of our choice of a Gaussian surface, then the electric field everywhere is going to be parallel to dA, because dA is always outward and perpendicular to the sphere. So that comes out of the integral. And so when I do E dot dA, that simply becomes E times the integral of dA, and I'm talking about a sphere. And that's equal to the charge enclosed. I know, kind of repetitious, right? Except for, this is the hint for that FRQ in gravitation. The charge that's enclosed by our Gaussian surface is going to depend on where we are, how big our surface is. So this depends on R. And how so? Well, let's suppose, and this is really similar. So while I'm developing it, I want you to also think about this question that's on an FRQ, where we drill a hole all the way down through a planet. So planet with a hole. Right, so does anybody know this? What's exactly on the opposite side of Earth from Essex, Vermont? Yeah, that sounds about right. Off of Perth. All right, thank you, Andrews. All right, so if we drill the hole all the way down there, then yeah, the Indian Ocean is going to start draining into this hole, and the water is going to squish back and forth. Of course, it's a molten core, so it's some problematic, but yeah. Yeah, so now we have this planet with a hole in it, and we're asked to find out what the force is going to be, right? So we know the gravitational force is going to equal minus big G, big M, little m, because here's our little m right here, over r squared. But m depends on r. It's a function of r. And you know what happens if this turns out to be a linear function? What happens? If this turns out to be a linear function of r, and then over here, we've got d squared r dt squared with a minus sign, we get simple harmonic motion. And whatever's in front of the r is omega squared. That's the hint. Right, so we have an m up here. M d squared r dt squared is going to be equal to minus, and then some stuff, and then r, and there'll also be an m over here that cancels. So whatever's in here, in this magic box, is also omega squared. So that's how you can figure out how much time it takes to oscillate back and forth. Okay, now let's see what that function is going to look like. What is Q as a function of R? Well, if we've already made a definition that the total Q can be used to define a volume charge density, so that's going to be Q over the volume. Then I can just use whatever volume I've got inside my Gaussian surface and multiply that by the density. So that's going to be rho times, and the volume of my little Gaussian surface is going to be 4/3 pi little r cubed, right? There we go. M is a function of r. Charge is a function of r. Right there, right there. And so if this is a function of r cubed, then that's where the linear term comes out. You see that okay? All right, good. All right, so we're ready to roll here. Let's go ahead and substitute this in. We're talking about the surface area of a sphere. So this is going to be that E is equal to the surface area of a sphere. Whoops, sorry, I'm not quite ready for that yet. So E is equal to, let's see if I can salvage this. No. So E, surface area of a sphere is 4 pi r squared. It's little r, not big R, because we're still inside our Gaussian surface. And then that's going to be equal to Q enclosed over epsilon naught. So this is going to be rho times 4/3. There's our epsilon naught showing up, pi and r cubed. Okay. So we have some cancellation showing up here. And if I go ahead and just follow through this, so the 4 pi's cancel out, and then 2 factors of r cancels out. So the electric field inside is going to be equal to the density over 3 epsilon naught. And that's a totally okay way to write this. I have 1 factor of r left over, sorry. So if I was actually going to plot the electric field as a function of r, what I would get is, and this comes up quite a bit. So I'll just label this as big R. This is the radius of my spherical insulator. And so inside, the electric field grows. So the electric field on the inside is 0. And then it grows in a linear way till we get to the surface. And then outside the surface, then it falls away like it was a point charge. So this is proportional to 1/r squared. And then here, it's proportional to r. It's a linear function. Okay. Now, sometimes what we have done, or what you'll see also in the literature, is that we'll reverse engineer this for density and put a Q in there instead. So if I was to solve this for density and use big R, the density is equal to, let's use the big R then, the overall Q divided by 4/3 pi big R cubed. Now, if I stick that in here, then my electric field is going to be equal. This is just a different way to write it. We'll substitute this in for density. The 3 is going to go, and then in the denominator, I'm going to have 4 pi epsilon naught. Oh, that's familiar, right? So I'm going to have 1/4 pi epsilon naught. Okay, so the 3 is gone. I've got epsilon naught. I've got the pi. And then I have r cubed. And I have big Q. And I still have an r right there. Right, so this would be 1/4 pi epsilon naught times Q times r over r cubed. And why is this important? Because when little r becomes r, then the 1/r squared function takes over. Right, so the value of this location right here of the electric field is going to be equal to 1/4 pi epsilon naught times Q over big R squared. Right, so this is kind of an interesting, call that a boundary condition. So the two functions meet and they have the same value. Right. That doesn't necessarily make this a continuous function though, right? So if it was a continuous function, their slopes would match up. But that's not the case here. And it's not really a bad thing, but it's just one of those things when we're trying to come up with models that change from one location to another, something to think about. How are these functions going to meet up? Okay. All right, one more. Spherical 2. And then I think we'll be good. We can take a break. And I see a couple of things on the, yep. That is exactly what I'm saying. So the question was, aren't we saying that in this situation here, that let's suppose our object is at this point, and here's the center, that the gravitational pull only depends on the mass that's between it and the center. And the mass that's outside doesn't count anymore because there's an equal pull from the mass above and the mass below. Yeah, because you know why? The gravitational flux is 0 for the mass that's on the outside. And that's the power of this flux argument. Right, so the same thing applies here. Since all this charge is on the outside of our surface, then the net flux is 0, and so it doesn't contribute. Yeah, that's really, so notice how these, both in gravity and electrostatics, these both show up. That's one of those, it's like seeing those connections. Connection here is, no, I don't have to worry about the stuff on the outside. It's only what is inside that counts. Q enclosed, M enclosed, same thing. Good. All right, good. So we've taken care of that. All right, one more to do today. And this pretty much covers all of Gauss's law. What we're going to spend time on Monday is we're going to take a look at applications, and a lot of them are going to be based off this. Spherical 2. And this is a thin hollow shell, a thin spherical shell of charge. Now, the reason why this is important is because this is what happens when we have a conductive sphere. So let's pause and think about this for a second. So here's a big sphere. You probably spent a little bit of time with the Van de Graaff generator last year. Does that ring a bell? So you have this giant dome of metal, and what happens when we place a charge on it? What happens when we place two charges on it? They're going to repel each other, and they're going to try and get as far away from each other as possible. So when we have a conductive sphere, all the charge resides on the outside. And that has big implications for Gauss's law, because if we have a Gaussian surface on the inside, it's not going to enclose any charge. That means the electric field is 0. Because these charges continually try to seek equilibrium, and they try and get as far away from each other as possible. And if they're not in equilibrium, they'll find it. If they're not in equilibrium, Coulomb's law will make them repel each other. That's why people who are experiencing electrostatics, why their hair stands up, is because their hair is all equally charged, and they're trying to get away from each other. So the only way to go is up. So all charge resides on the outside. Okay, so inside, we apply Gauss's law. Electric field E dot dA is equal to Q enclosed over epsilon naught, but this is 0. So the electric field is equal to 0 inside the conductor. That's a big statement. The electric fields are always inside. Inside conductors, the electric field is always 0. And then when we go outside, our Gaussian surface is again going to be a sphere. But since it's a sphere, E is parallel to dA and constant, so it comes out of the integral. So then I just have E surface integral of dA over a sphere. And that's equal to Q, whatever the whole charge is, over epsilon naught. And the sphere is just 4 pi r squared, so E times 4 pi r squared equals Q over epsilon naught. So our electric field is equal to 1 over 4 pi epsilon naught, there it is, which we also know is K, 9 times 10 to the ninth, times Q over r squared. So now it's behaving like a point charge again. And so now when we plot our electric field, there's a bigger discontinuity that inside the radius, the electric field is 0. And then when you hit the outside, bam, then it jumps up and then falls off as 1 over r squared. Right? Yeah, so that's interesting. So if the Earth was hollow, then the entire inside would be 0 gravity. Yeah, the whole of the inside would be 0 gravity.
So the reason you're applying these analogies is because, like how can you make that connection with like gravity to electricity? How do you know that?
Yeah, that's a great question. Pat's asking the question, how come we can always keep making these analogies between electricity and gravity? And the answer is they're both inverse square laws. So their topology is the same. Topology is a really interesting field because it talks about dynamics between variables, and it's really fascinating. But electricity and gravity have the same topology, which always fascinated Albert Einstein, and he never really got it to work. And so it's one of those big question marks that's still out there about how can we actually resolve these two forces? And again, you know, it seems to come back to this idea about why there isn't negative mass. Where's the missing mass, you know? Like, what's up with that? And so maybe it'll happen in your lifetime. And if we do figure it out, you might be able to use it to have a new kind of force to push yourself through the universe, which would be amazing. Yep, Scott asked the question about, is it true for positive charges and negative? Yes, they are free to move. And if they're free to move, they're going to try and get as far apart from each other as possible.
Is that what you're saying? I think the positive charges which repel each other. I'm not sure.
Yeah, so the notion of positive charges just means electron holes, really. So that's one way of thinking about it. Just absence of electrons. Yeah, last year they said that only negative charges move, and that's what I said in the beginning of this unit too. But again, the absence of an electron can be considered a positive charge. No, the electrons will push it. If it has a net negative charge, all the electrons are going to move as far apart as possible. Yes, right. So these are all these atoms are have valence electrons that are easy to move. So they'll just be passing electrons around so that the ones that don't have that valence electron are as far apart from each other as possible.
All the negative electrons.
Yeah, it'll still have all these electrons. It's just The places where they're not will be equally spaced apart. Let me just, I don't know if this is going to help, but do you remember electron dot? So here's silicon, right, which is a famous semiconductor. And this is silicon's directly underneath carbon on the periodic table, right? So do you remember how many valence electrons it's got? It's famously got 4. 4 is amazing. So silicon is an extremely abundant element on planet Earth. Sand. And if you put another silicon right next to it, then what happens is we start to get an electron structure that looks like this. And if I put another silicon in here, then I get an electron structure that looks like this. And so these two match up, and so this is filled. If I kept on going with silicon around here, then the shared electrons are actually going to fill up and make an octet. So to talk about how to, how do positive charges move then, if one of these was shy an electron, then we would call that a positive. And if there was another missing electron somewhere, another electron hole, another positive charge, then they're going to try and move as far away from each other as possible, because any neighboring electrons are going to want to come in and fill that hole. So in sort of like a domino effect, the positive charges wind up propagating to the outside. Okay, so hopefully that helped a little bit.
Is that always happening at a set speed, or does it depend on how many particles there are?
It depends on the material. The question was about, does it depend on what does the speed depend on? It depends a little bit on the material. But this combination is really amazing. And if you take the elements that are next to silicon on the periodic table and you add a little bit of those as an impurity, you can actually intentionally create excess electrons or holes. And when you put them together, then you have what's called a semiconductor or a diode, which is the birth of a transistor. And most calculations at this point say with the propagation of cell phones, there are more transistors in the world now than there are leaves on trees. So yeah, so if we have a little bit of time, we'll talk about diodes and transistors, but it's really fascinating. And you can use them to add. So that's why adding in binary is relatively easy to do with electronics. Hundreds of millions of transistors in this room. And the other issue, so this is one of the huge Nobel Prizes. This is discovered by Bell Labs in 1951. And once the skill, the technique in order to really control the impurities that you're adding to silicon, we can make what are called N-type materials and P-type materials. And when you put them together, all sorts of magic happens. So that we can actually control the flow. It's not just electrons going from positive charge to negative anymore. We can control them. All right, well, that was a lot. But at least you'll be able to come back to this. We're going to keep on referring to this. We talked about some really fundamental properties of these charge distributions, and everything that happens from here on out are just going to be riffs on these basic symmetries. Okay. Any other questions online that I didn't get to? All right, good. All right, well, that's the end of class. I'm not going to assign any homework because I just put up that massive gravitational FRQ. But if you get a chance to, before this gets too cold, I would go handle the very first one. It's about the oscillating planet. All right, cool. Ooh, blank slate for next time. Actually, next week we have a couple of labs. So I'm going to do a lab with blue and a lab with gold. And during those days, it's not going to be necessary for, if you're in a remote cohort, that'll be Tuesday and Thursday of next year. You don't need to log into class. It'll just be for those 2 days. So
I think that's a property of inverse where
yeah, so let me see if I understand your question. You're talking about an electron in orbit, let's take a hydrogen atom, for example, right? And so here's one of the issues with that. I'll just do a quick sketch. So here's our hydrogen atom, right? And an electron out here. The so-called planetary model. Okay, so this doesn't really work because on something that's accelerating like this, so the electron would have an acceleration, and it's going to lose energy when charges are accelerated. They give off light in the form of photons. And so a planetary model doesn't work in this electricity idea because it winds up spiraling in. So thinking about a velocity doesn't really work. What we instead need to think about is that this is sort of the wave particle duality. So the electron is not really an isolated particle. It has both wave properties um, and particle properties. And this was one of the big ideas that led to the Bohr model of the atom, is that only specific orbits are quantized and it depends on what their momentum are. So in the planetary model, any orbit is possible, right? So in quantum, only certain orbits are allowed. And that's based on, the orbits are based on what their angular momentum is. And that's exactly, goes back to chemistry, those sp and d orbitals, those are the only orbits that are allowed. Yeah, very interesting. This took people a really long time to resolve. Huge debate at the turn of the 20th century about planetary versus wave particle duality. Because the issue is, then how do you write this thing as a wave then? You know, how do you write an equation of motion that's also a wave? So it's and you have to do it by adding harmonics together. So what it is actually a localized wave packet like this. And you can achieve that by adding a fundamental frequency so that this has energy equal to Planck's constant times the frequency. And the momentum would be C over lambda, I believe. But you can get this by, you start off with a fundamental frequency, then you add the next harmonic in with specific coefficients, and you keep on adding it, and you can wind up getting this wave that only exists in a finite location. So it's got not only a wavelength, but also has a location. And so then we start talking about the probability of where this thing is likely to be. That's why Einstein didn't really like quantum mechanics, is because it was based on statistics and not, you know, fundamental mechanics tends to be really deterministic. But when we start doing this, then we're really talking about, so where's the electron really? And so we would say it has a probability of existing somewhere in here, but it could actually be out here. And that's where quantum tunneling comes from and all those things. But this is fun mathematics. This is actually when you do this e to the I theta thing I mentioned before. Yeah, that's the basis for how you can actually generate wave functions like this. And you can do it numerically too. Guess how you do it numerically? You use a Taylor series expansion. Yep. It's all there. And just scratching the surface is kind of exciting, right? I tell you, if you're into it, a math minor is always something cool to have. All right. Yeah, we're all done. That all that stuff just came out by a quick conversation here in class. But we're all set. Feel free to log off. Hope you have a great weekend.
Actually,
Yeah, and Scott, you're exactly right. It doesn't really matter whether it's positive or negative. Yeah, that is the whole point. Okay.